Our work is about fair resource allocation in federated learning, and this is joint work with Mars and Matt in Virginia. Federated learning is privacy-preserving training in heterogeneous and potentially massive networks, like a network of cell phones or hospitals. It has many applications, like voice recognition on mobile phones, predicting pedestrian behavior on autonomous vehicles, providing personalized healthcare with wearable devices, and predictive maintenance on the sensor networks deployed in industrial machines. A typical objective we'd like to solve for federated learning is to fit a global model W by minimizing a loss function, which is a weighted average of the local loss. Fk denotes the loss on device K and Pk is the weight. However, minimizing such an aggregate function may disproportionately advantage or disadvantage the performance on some devices. There is no accuracy guarantee for individual devices in the network. The data are often heterogeneous in such settings, both in terms of size and distribution, and the model performance can vary widely. And therefore we ask, can we devise an efficient federated optimization method to encourage a more fair, that is more uniform distribution of the model performance across devices? And we propose a novel optimization objective that addresses fairness issues in federated learning, and we call it q-Fair Federated Learning, or q-FFL for short. q-FFL minimizes an aggregate reweighted loss parameterized by q, such that the devices with higher loss are given higher relative weight. And this objective is inspired by alpha fairness for fair resource allocation in wireless networks. It enables flexible fairness accuracy trade-offs through a tunable parameter q. When q is equal to 0, q-FFL recovers the previous objective, and if q is large enough, it reduces to classic minimax fairness, where the goal is to minimize the loss of the worst performing device. In terms of theory, we provide generalization guarantees for q-FFL and also prove that increasing q results in more uniform accuracy distributions based on the uniformity measures we define, such as fairness. For example, we examine the accuracy distribution of a model trained by the baseline approach and q-FFL. Due to the variation in the data across devices, the model accuracy is quite poor on some devices. By using q-FFL, we can maintain the same overall average accuracy while ensuring a more fair accuracy distribution across the network. Solving q-FFL in massive federated networks is also challenging. In order to trade fairness between accuracy for different applications, we often need to train a family of objectives with different queues. This may cause the search space to explode. In addition, federated networks are heterogeneous with extremely expensive communication. And we propose a lightweight and scalable distributed method to solve q-FFL to handle these challenges. At a high level, it dynamically estimates the step sizes associated with different queues to reduce the overhead of tuning the hyperparameter queue. It also allows for low device participation and local updating, which have been commonly adopted for federated optimization methods. And here are our main empirical results. We use a benchmark dataset we developed called LEAF. Under Q values larger than 0, across all datasets, we have similar average performance compared with the baseline. But the variance is decreased significantly. By setting Q to be larger than 0, the accuracy of the worst 10% devices is increased at the cost of possibly slightly decreasing the accuracy of the best 10% devices. On average, q-FFL is able to reduce the accuracy variance by 45%, and our solver solves the objective orders of magnitude more quickly than other baselines. Besides q-Fair Federated Learning, in this work, we also demonstrate that q-FFL can be applied to other settings such as mental learning. We empirically demonstrate that q-FFL helps produce fair initializations across multiple tasks on the omnigular dataset. And more broadly, q-FFL is a generalization of minimax fairness and can be used as an attractive alternative when minimax optimization is hard to solve. And finally, you can also find the code and paper on my website or on the Open Review. Thanks.